All right. So hello everyone. My name is Aldo Garcia Guinto. I am a student of Brent Nelson here at MSU. And today I'm going to discuss about standard forms. The idea is that this should give you the ability to read some papers that have to do with tracial von Neumann algebras, since this is the setting which will mostly be in here. So I've given you the definitions for faithful, normal, and tracial, which is the things that we're going to be needing. So we'll start with the definition. So a pair M tau is tracial if M is a von Neumann algebra and tau is a faithful normal state. Which we call a trace. Okay. So a nice thing about tracial von Neumann algebras is that, sorry, this is supposed to be tracial von Neumann algebras. Um, so uh, is that they're automatically finite. So it is always finite. There's always a finite von Neumann algebra. If P is less than 1 and sub-equivalent to 1, then you know that you have an partial isometry which encodes the data of P in 1, and because of that reason, you can show that P is equal to the trace of 1. So the sub-equivalence is telling you this. Sorry, not sub-equivalent, but the equivalence is telling you this, and by faithfulness, P is equal to 1. And this is just mainly because 1 minus P is a positive element. Okay, so of course the question then boils down to is the converse true? Sadly, it's not, so we're going to give you a fact. So M is a finite von Neumann algebra if and only if there exists a unique center valued state. Sorry, center valued trace. Tau goes from M into the center of M. So this fact is proven in the Goals notes. If I'm correct, it should be chapter 5, section 4. And in particular, what happens is that if the von Neumann algebra is a factor, so this is a corollary 5.18, if M is a finite factor, sorry, M is a finite factor if and only if there exists a unique trace. So this is a linear function of tau from. So the uniqueness is what comes from coming from the fact that you have a factor. Okay. So from now on, we're going to fix a tracial von Neumann algebra. And we denote we can construct the GNS representation, so denote the GNS Hilbert space. And the inner product here comes from the following. So x comma y to the trace. And so L2 of n, just to remind everybody, this should be equal to the norm, the closure of this one here. And this is called the 2 norm. So the 2 norm of an element will look like this. I'm calling it a norm because of the fact that tau is faithful. So this is a norm since tau is faithful. Okay. So the following result was probably proven in the C-star lecture, but just for completion, let's write it down. So for any x and y, we have the fact we're able to bound the 2 norm. So in particular, this means that the norm of the 2 norm is less than the operator norm. Let's prove this. So we already know by the C-star lectures that this element is bounded. Oh, I can, by the C-star identity, I can put this in squared here. We know this to be true. Then the trace this is just equal to the trace of y star, x star, x. And then just taking the square root gives you the proof. Finishes the proof. So this is going to, so the first things I want to note is that for any x and m, we will denote the vector by x hat, and this is going to be living in the GNS representation. So in other words, the GNS representation contains m, and in particular, because of the theorem that we have above here, we also have a representation. So we can define a map. So pi tau going from m into the rounded operator, so this is Hilbert space defined by and the reason why we're able to define it like this is because m hat is dense and the operator and this operator is bounded by the norm of x here. Okay. So one thing to note here is by the C-star lecture notes. Sorry, by the C-star lectures, you have seen that pi tau is faithful, which mainly comes from the fact that tau is faithful, and it's normal because when you look at pi tau of x y hat,
C hat. This is equal to the trace of C star X, Y. So the way that you should think about it is that if you have a net converging to X, multiplying it from the left by an adjoint and by Y doesn't change anything. And the fact that tau is normal gives you the normality of pi. So we have that pi tau is a faithful normal representation. And representation just means a map from an algebra into some Hilbert space. Okay. Because of the fact that it's faithful, we can just identify it. So identify M with its image and identifying this, it follows that M is a von Neumann algebra, the bounded operators. And this is the way that we're going to write the operator now. So in general, in some papers, they don't have the y hat, but usually it's not too difficult to tell when an element is being thought of as a vector over an operator. But this allows us to not have to worry too much about that. So then this leads us to another definition. It's 5.1 point, oh, 2.1, sorry. The representation is called the standard form. So the standard form pretty much is saying it's the action or representation into this Hilbert space. And you might be asking why this is so relevant. And the idea here is that inside the standard form, you have a nice way of witnessing what the commutant really looks like. And that is one of our goals to do in this lecture. But before that, it should be nice to look at some examples. So some of the examples that we've seen. Whenever in doubt, you should always check something in the matrices, mostly if you can. So the standard form of M, and we remember that because of the fact that I want the trace to send one to one, this needs to be normalized. So the standard form is just the matrices. This is an exercise, exercise 5.2. The other example is, of course, discrete groups. The standard form of a group polynomial algebra with its canonical trace is L2. Okay. And this is exercise 5.2.3. And here gamma is discrete. Write that down. Okay, so as you saw also in the C-star lecture notes, well, it's a little bit harder because in our case, remember that because we work with von Neumann algebras, our von Neumann algebras have the unit. And so we can see that one hat is in L2 of M is cyclic and separating. It's cyclic because X hat is going to give you X hat, and M hat is dense.
Separating comes from, if I haven't said it enough, I'll say it one more time, faithfulness.
And this is because we know that X one hat,
The norm of this vector
is equal to the square of this vector is equal to the trace of X star.
So notice so far that everything that I've done, this is going to become important in the next lecture that I give on Thursday. Notice that everything that we've done up to this point doesn't use the fact that we have traciality. This just uses the fact that this is just a GNS representation, and so one hat will be cyclic and separating in these cases. This is the first instance. Well, this is going to be when we use traciality.
So for X and M, define the map
X tends to X hat. We're going to show that in M hat, this is going to be conjugate linear.
So let's look at what it does to regular vectors, J. So this is going to be X hat star, Y star hat. Using the trace, this gives you Y X hat. Y X star. And then traciality here gives us the trace of X star. Okay.
And this is what it means to be conjugate linear. It means that like when you apply it, it flips the terms. In particular,
If Y is equal to X, this is just telling you that J hat squared is equal to X hat squared.
and this is telling us pretty much that J is bounded. J is a bounded operator.
So thus,
And it's not just bounded, it's an isometry.
thus J and because it's an isometry, we can extend it. So thus J extend J uniquely to conjugate linear isometry. Oh, two of them.
Which we still denote by J. Okay. Notice that
For any vector,
you don't know what this looks like. You have no idea what this looks like. You only know what it does to elements on M hat. Okay, so just
something to note. And then now we're ready for our next definition, which is
the name of J, pretty much, which is just the conjugate operator.
So now let's look at some observations. The first thing to note is that for x and y, uh, jxj, y hat is equal to jx y star. And then this is just yx star. It's gonna become useful to work with this, but the main idea, the other observation that we have is that for any operator, jxj star is equal to j star. This is an exercise. So I'll leave it for you guys. And then the next thing is to note, you might be asking why this element is so important. And the reason why is because JMJ is inside the commutant, inside the standard. So J X J Y C hat. So this is the same thing as XJ. YC hat, and then we have this computation above to let us know that this is the same thing as YC X hat. Oh, sorry. YC X star hat. And we can bring out the Y. And again, by the computation above, this is just the following. Okay. So a question that probably comes up a lot is why am I only checking this in the in M hat in this dense subspace? And this is mainly because all of these operators are bounded. And so what you would do is then you would do a density argument to show that it's true for everything. Okay. So our goal, well, one of our goals is to show that the converse is actually true. But to do that, we need to recall the idea here revolves around a notion of left-boundedness, which we saw in the discrete setting, in the discrete group setting. So given a discrete group, we looked at left convolvers. So these were operators in L2 of M, sorry, in L2 of gamma, such that when you looked at the convolution, this is going to be a bounded. Is going to be bounded. The reason why in this case you're able to define this in this kind of neat way of using the convolution is because you know how the elements in L2 of gamma look like. You have a real way of controlling the operators, the vectors. In this case, we don't. So we do not understand L2 of M in general. And so, but we still want to be able to define an action in the similar way that we define this action here. And for that reason, it suffices to ask for this to hold at the level of M hat. So we have a definition for C in L2 of M. We define the following possibly unbounded linear operators. So lambda C. And so we call in the same light of left convolvers, we call left bounded. So lambda C is left bounded if lambda C can be extended to an operator on L2. And similarly, right bounded. Right? You just want rho instead of lambda. Of course, the extension is going to be denoted the same way. We're going to denote it by lambda c and rho c. And then L of p, this is going to be lambda c, such that lambda c is a left convolver, is left bounded, sorry. So maybe when you look at this, you're like, that's a weird way of writing the element. And the idea is that we want this to look like you would suspect, or you should suspect, the lambda of x hat should be just x, right? And so let's show that. So given this in y, this is equal to jx hat jy. The computation above, oh, I wrote this in the wrong order. That's why it should be y hat x. So this is equal to j y star x star hat, which is equal to x y. And then again, by density, we have the lambda x hat is equal to x. In particular, this shows that M is contained in the left bounded left bounded. Feel like I'm gonna keep saying convolvers as a habit. Okay, so we have a proposition. So in here, we're just gonna mention how the adjoint looks like and stuff like that. So give this. Okay. And then in particular, what this shows, which way do I want to say it? Nah, I don't want to say it that way. Moreover, J left bounded is equal to right unbounded. Oh, it's funny. And the left is contained in the commutant of the right ones. Feel like I have it time for a little piece of the proof. So this proposition is this is proposition 5.24. So you can go and look at the proof. So I guess yeah, I'll just leave it behind. I'll just leave it like that. Yeah, the proof is not too bad. It's just a bunch of computations that are pretty straightforward. Okay. So now we're ready to write our main theorem. Theorem 5.25. Remember, we're still in the setting of a Tricia von Neumann algebra, so representing b about 2. We have Jm J is equal to m prime in the space. Okay, so this one I am going to prove, but this uses the proposition above. Okay, so as we saw already, we have m is inside of LB. We're going to show that the right-hand side, well, I'll just write it down. So for m hat, sorry, for x in m hat, sorry, not in m hat, for x in m prime and y in m, we have that row of x 1 hat y hat. This is equal to y x, oh, it's 1 hat. But y and x commute. So we end up getting x y hat. Notice that I had to write x 1 hat because we don't really know how that vector looks like. But this shows us that row of x 1 hat is equal to x for x in m prime. That m prime is a subset of the right bounded. Okay. So the proof that I'm going to use now is the similar proof that you used in the case of in the discrete setting, in the discrete group setting for the left and right convolvers. So now we know that m is contained in left bounded, which is contained in right B bounded prime. And this switches the order. So this is going to be prime of prime, which is equal to M. So this implies that M is equal to left bounded and also equal to the right BM. And then now we can argue the same way, but with primes. This is going to be R BM. This is, of course, contained in M prime. Prime here. And this is equal to, by the above, M prime. Which implies that M prime is equal to R BM equal to LB. Okay, not so bad. Now, if we go back over here, we see how they interact. So, how does this go? Maybe like M prime? Yeah. So M prime is equal to R BM. And this is just equal to J LB of M. But by the above, this is just equal to M. Finishing the proof for us. And if you go back to the left convolver case, you'll see that this is exactly the same proof. Nice. Now, one thing to note here is that probably should show the proof. So if M tau is a trace of polynomial algebra, then so is M prime intersect U of L2. Right? Given by the using the J's, right? Because when you do J, when you conjugate by J, you'll be able to get back you'll land on M. In particular, this tells us if M is a finite factor, then you have a unique trace, and using the same construction as above, we have that M prime is also a finite factor. Again, only in P of L2. Right? Like this is not going to be true in general. And that is the example that I'm going to give you now, is an example where M is tracial, but M prime is not tracial. So consider M tau tracial polynomial algebra and M tensor 1 acts on L2 of M tensor H, where H is infinite dimension. I don't know if you guys have learned what M tensor 1 means in this case, but the idea is the following. The action is given by this. So given X tensor 1, acting on a pair of vectors, C tensor eta. This is just, you only act on the first coordinate, on the first tensor, on the left tensor term. That's why you have like an imaginary one. So here C and eta are It's in L2, and eta is in H. Then the commutant of M tensor 1 is equal to M prime tensor P of H. Or also JM J tensor P of H. I think this is an exercise actually in the goals notes, if I remember correctly. I forget where, probably when you first defined one Neumann algebras. But yeah, nice, nice. So notice that in this case, this is not a trace of von Neumann algebra, and yeah, mainly because of B of H is there. Okay, so now in my last few minutes, I will be discussing about the conditional expectation, which will be needed for tomorrow's talk. Definition. Let yeah, so let these be C-star algebras. A conditional expectation. Um, sorry, it should be the other order. B. So we need some conditions. The first one is that it leaves the elements of A alone. The next one is this kind of like bimodule structure. And then the other thing is it needs to be positive when you feed it a positive element. Here, positive means positive in A, right? So keep that in mind. Oh, sorry, I should have. You're right. You're right. It's positive whenever A is positive. Okay. So there's a discussion that happens. So one let's see, one can show that the norm of this is equal to this. One can show that E is a contraction. This is discussion before theorem 527. And so probably one of the most important things to note here is that in general, a conditional expectation from a von Neumann algebra to a sub to a sub to a von Neumann subalgebra. Of course, one needs to be here. Does not need not exist. This is in the general setting. But the thing is, go
Wait, do
ahead.
you mind scrolling up for a moment?
Yeah, of course, sorry.
Use
So how do we define E of A1, B, A2 since we're multiplying elements in A by an element in B?
A is a subset of B. What do you mean?
Okay. Oh, A is a subset of B. All right, thanks.
No
That makes
worries.
sense.
Um, nice. Yeah. So conditional expectation. Well, okay. So I gave you the general definition of conditional expectation at the level of C-star algebras. But when you are looking at polynomial algebras, they don't need to exist. I'm pretty sure probably in C-star algebra it's probably true as well, but I don't really know. The thing is that the conditional expectation does exist whenever you're looking at trivial polynomial algebras. So this is the last result that we're going to cover. So theorem 5.27. Uh, let tau be a trivial polynomial algebra. If one is contained in N, there exists a unique, faithful, normal conditional expectation onto N such that no, yeah. Sadly, because of time, we can't cover this. This is in the goals note stuff. But just because I won't be able to cover it, I should at least tell you what the map is, right? So, uh, proof of idea or idea of proof. It's fine. Doesn't matter. So the first thing we do is we take a projection. So we use En. Into the subspace. Um, notice that uh, notice that this is actually equal to the L2 of N because the N trace restricted to N is a trace of polynomial algebra. And now we're going to see how En interacts with certain operators. So JEN commute. Oh, yeah, no, I wrote it correctly. Nope, I didn't. Since N is a star algebra, we also have that En commutes with Y for Y and N. And this is mainly because the Hilbert space L2 of N is invariant over N. It's invariant. I forget if it's in. Yeah, no, this is fine. Okay, and then you can show that lambda of En x hat is going to be a bounded, left bounded operator on N for all oh, for all um x and M. Thus, we define because of the fact that we showed before that the left-bounded operators of n is going to equal to n, this gives us an operator to work with. And so En of x is going to equal to lambda En of x hat, which is going to be an n. This operator satisfies this operator Enx. Also, x is an m. This operator satisfies so En x y hat is going to equal to well, yeah, this is fine. En x y. Or probably just feed it into it, so it should be x y. And this is just because you can peel off like the information from lambda En x hat, which we have above. So this is just like a straightforward computation. And yeah, that's all I had. So let me stop the recording.